Okay, so we are back and we start with a quick review of whatever we have done so far. So, what we have done is we have seen that this integral, which is taken between two stationary points of any function x, y and y dashed dx, if between two fixed point, if this integral has a stationary value, that means if it is following a path. By the way, these are all path integrals, so it is following some path c. Now, if this curve is such that this integral reaches a minimum or a maximum value, that technically means delta I equal to 0, then we have seen that this function f will satisfy this equation, which is in case of if f we choose as a Lagrangian and we replace x with time, y with q and y prime with q dot, then this actually gives you the Lagrange's equation of motion. This we have seen. So, that is the fundamental principle of variation, and also we have derived something called Beltrami identity, which was the end of the last class, which says if f is not an explicit function of x, the parameter x here, that means if del f del x is equal to 0, then f minus what was it? Yeah, y prime del f del y prime is equal to a constant c. Okay. So, it is a constant. So, this is the Beltrami identity. Now, this one we have already used in certain cases. This one we will take up and in the very next example. So, let us be back with the let us go back to the problem set. The problem number 3 says a mass m is falling under gravity from point A to point B, which are not on a vertical line. So, that means point B is not exactly below point A, but there is a gap. I mean, there is a horizontal shift. So, we have to use calculus of variation to determine the path in which it will take minimum time. Okay. So, if I try to draw a picture, a figure, it will be something like this. I have, this is my vertical direction. Okay. So, we have 2 points A and B, right, and they are not exactly on, I mean B is not on a vertical line. So, it could be anywhere, but not exactly at this point. Okay. It could be anywhere, and a particle of mass m is travelling from A to B. Okay. So, now what is the time, or what is the path along which the time taken will be a minimum? Now, intuitive answer is a straight line, which is not. Okay. So, if I just put a slope here, it will take some time, I mean some time, let us say t1. So, now if this is the case, if this if I put a straight line, I mean inclined plane, if it takes time t1, it turns out there could be another plane of some another curve which can join these two, and if it travels, the particle travels along this curve, it takes a time t2. So, it turns out that t2 could be less than t1, right. So, our job is to find this curve where along which the time will be shortest. Now, in order to do that, let us assume that to travel along this particular curve, we take a small segment of length, which is given as ds or dl, let us say. Okay. So, for the mass to travel this small length dl with a velocity v, the time taken is t is equal to, or dt is equal to dl by v, right. Length by velocity is your time. Okay. So, if we have to optimize, so the total time taken t is nothing but integration of dt between 2 points A and point B, right, which can be translated to dl by v. Now, if the driving force of this motion is purely gravitation, okay, if it is purely gravitation, and let us assume this point L has a vertical drop, it has a vertical drop, let us say dz or z, sorry. So, basically what we need to do is we need to find out what is the total vertical displacement of this particular particle, okay. And if this is z, then from Newton's law we can immediately get that V is equal to root 2g z, right, okay. So, this is something we are very familiar with, this is the familiar expression, and then what we do is, and of course, if this is z axis, this is my x axis. So, dl can be written as, or actually what we do is I am just changing it to y, because it will be easier to write, nothing else. So, this is this, and this will be simply dx square plus dy square, right. So, if I substitute this here, your time t will be integration a to p. Once again we can write this as dx root over 1 plus dy dx's whole square, right. We can do that, and once we substitute it here, we get dx by dx root over 1 plus dy dx's whole square divided by 2g y. So, we have to, so for the path, for the curve along which, and this is, for example, right now we have not taken any specific shape of the curve. So, dl is an infinitesimal length element, and we do not say anything about the nature of the curve at this point. But now, if the time taken has to be a minimum, that means this integration, I mean the delta t has to be equal to 0, which is exactly what we expect in variation principle. So, that means we have to calculate, we have to find out the expression of this curve f, which is simply given by, we have to find out the function f by solving this equation, where f is, or we have to find out the equation of the curve, which is of the form y is equal to y of x, by taking this as my function f, right. So, this is how, this is where we end, or this is where we come finally. So, I will just remove this figure, I will draw it again if necessary. So, f of x y prime is this one, which is given by 1 plus y prime square divided by 2 g y. And now comes the Beltrami identity into the question. See, f is not an explicit function of x. So, that means del f del x is equal to 0, and from Beltrami identity we know that we can write it in this particular form. We can use this identity actually. So, what we can do is we can calculate del f del y prime, which will be the expression y prime square by 2 g y whole to the power minus half times 2 y dashed, right. So, if I have to compute y dashed times this, so it will be 2 y dashed square, and f minus this will be 1 plus y dashed square 2 g y to the power half minus 1 plus y dash square by 2 g y to the power minus half multiplied by 2 y dash square equal to some constant c. Now, if we start simplifying from here, and I mean this will be just pure algebraic simplification. We can do that. If we do that, we will end up with the following expression. I mean this is just a lengthy process, but not much to be done here. So, finally, we will end up in this particular expression root over 2 g y, it will be 1 plus y dash squared. It is basically 2 steps of algebraic calculation equal to some constant C 1. Okay. So, we can do that, and from here we can slightly modify this once again, and we can write this final expression as, or final differential equation as dy dx equal to root over 1 by some constant k y minus 1, right. Okay. So, if you wish, we can write it as 1 minus k y by k y, right. So, this is the final differential equation we have to solve in order to get y as a function of x. Now, it turns out the solution is also I mean its solution is also very standard. The solution is I mean it is not very difficult, you just have to do a proper substitution, you can do that, we all know how to do this. So, if you do this, the final expression will be half k square theta minus cos theta, and y is equal to half k square 1 minus cos theta, sorry this is sin theta not cos theta. Right. So, this is my final curve. So, if the particle travels in this particular along this particular curve, which will be, which we can draw. So, it is the equation of a cycloid. Okay. This family of curve is called a cycloid. What is it and how is it, I mean how does it look, we will see in a moment. So, it is some curve. So, the thing is, if I go back to my original picture, I have point A and point B. If it follows a curve, which the equation of which is given by this, under gravity, purely under gravity, an object of mass m which is sliding down this curve will take minimum time to reach point P. Okay. Now, sorry, CYCL, sorry my handwriting is not that great, I know, cycloid. Now, how does this curve look like? This is a curve, as you can see there are periodic functions in you know both of them. I mean you can take theta as a parameter. What is theta? I will come back in a moment. Theta you can take as a parameter, and you can see there are sin thetas and cos thetas in both the expression of x and y. Now, if you draw this in a more formal manner, this curve will look something like this. Right. See, if you put theta equal to 0, the first term is 0 minus 0, so it is 0, and the second term is 1 minus cos theta at theta equal to 0 will be 1. So, at theta equal to 0, both of them are equal to 0. Similarly, if you put theta equal to 90 degree, you will see that this is pi by 2 minus 1 and this is 1 minus 0. So, it has some value. Similarly, at theta equal to pi, you can find out it will go back to 0, I guess, once again, yeah, because 0 minus something minus no, it will go back to 0 at 2 pi only. So, along this curve theta is also changing. Okay. So, if you take, this is my x and this is my y, theta is also changing in this particular direction, and this curve will, if a particle trace out this curve, it will look like this. Now, what is the physical interpretation? First of all, it can be shown that this curve is the locus of a point on a wheel. What I mean by this is, let us assume that there is a wheel here of certain radius r, right. Let us say this height will be your k, I guess, right. Okay, so I am not sure, so I will not write anything, but let us assume that there is a wheel with this radius, let us call this h, okay, wheel of this radius. So, the wheel looks something like this, or sorry, this diameter, not radius, the diameter. So, the wheel looks something like this, and let us say the wheel is moving in this particular direction, right. Now, let us say this is the point which, this is the position of one point on this wheel. Now, as the wheel rotates, what happens to this point? See, when you rotate it in a next position or in a later position, your wheel, okay, I will use another color, maybe that will be easy for you. So, this was my wheel at time t equal to 0, and now at a later position, let us say here, this is my wheel once again. Now, what happens to this point? This point, as this center has shifted from here to here, this point also will be shifting, and it turns out this location, I mean locus of this point will always stay on this curve. Okay. So, at this point you can say without drawing anything that this particular point is here. Okay. So, it has moved along this curve. So, this is the concept of a cycloid. Okay. A cycloid is essentially a rotational motion, I mean it represents a rotational motion, but it is not a rotational motion in the conventional sense, it is more of a, I mean it is like one point on a wheel, the locus of that particular point, if we trace for the standard translation and rotation motion of a wheel, that point will trace out this particular curve. So, I have prepared two, by the way, this problem is called the Brachistoctrone problem. So, Brachistoctrone, I think the spelling is correct, let me have a look. Brachisto, CH, no, just a minute, the spelling is not right. Kiss, Brachistoctrone. Okay. So, the word, it is a Latin word, brachis means short and chrone is time. You know the English word chronology, which means the time bound documentation of certain thing. So, that chrone is that has the same origin from this word chrone. So, this problem means the problem of short time. Now, I have prepared a slide for you, Here you see there is whatever I have discussed in the board just now, it is there. So, it is the locus of this particular point which is traced out in the space, and this will draw, this will, I mean this particular locus of this particular point will trace out this curve. And in this link, I have given an hyperlink here. In this link there is a beautiful description of how you can get to the same equation using from the Fermat's principle, drawing an optical analogy of the system. Please go through it. I will also try to describe it in very brief. And also there is a video, if you search Brachistoctrone in YouTube, you will find this video as within first one or two links. And this is a beautiful video. In this video, there are model toy cars present, okay, and there are two slopes, two channels which has been, one is a straight channel and the other one is this basically it is a Brachistoctrone channel. So, what they did in this video, what they have demonstrated is they are releasing these toy cars from the top of this exactly at the same time, and it is very clear that this one the car which is travelling through this arc is reaching the ground at an earlier time. Okay. So, this is a beautiful video. If you look at this video, you will be little more convinced that it is actually not a straight line. Also, I talked about an optical analogy. You can just a minute. Yeah. So, what they have given in that particular website, I will just try to describe very briefly without writing any equation. So, a Brachistochrone curve can be, see what happens is Fermat's principle of least time says light travelling between any 2 points takes the shortest time. Now, think of it, light is travelling across an interface. You have n1, you have n2, and n2 is less than n1. So, basically lighter medium, light is going from lighter medium to denser medium to lighter medium, right. And we all know, according to Snell's law, it will be an refraction phenomena. So, light will be moving away from this axis. So, if this is your theta 1, this is your theta 2, we know that Snell's law n1 sin theta 1 equal to n2 sin theta 2. Now, what happens in Brachistochrone is this: we have a point here, you have a point here, and an object moving in a path which is like something like this. Now, think of optical medium. Okay. So, what is the main idea? Where the analogy comes? From here to here, if I consider a point A here and point B here, light, according to Fermat's principle of least time, light takes the shortest time to reach from A to B. It is, although it is not a straight line path, okay, it is not a straight line path because there is a refraction happening. So, even in this curved path, light takes the least time. Now, if I add many more levels, let us say this is my point A, this is my point B, okay, and what we do, we add many more levels of material. It is an hypothetical experiment, for example, many more levels where the density is decreasing in this particular direction. So, or rather I should put the arrow up. So, as we go up, the density is increasing, and as we go down, the density is decreasing. So, if a light ray starts from this particular position, what will it look, the path of it at each of the interfaces, it will deviate slightly more and more and more and more. Eventually, after many deviations, it will reach point B. So, even if it is not a straight line, it will take the shortest time according to Fermat's principle, right. And if I now draw an analogy between the speed of light in one medium V n with this law of whatever we have derived from gravity, whatever velocity expression we have used in solving the problem classically, that analogy is something you can, if you read that website, you can read that link, you will be able to understand. And then in the continuous limit, the equation of this curve or the differential equation which will produce this curve will be exactly give you this exact same differential equation which gives you the final Brachistochrone curve or final cycloid. Okay. So, this is how an optical analogy. So, this is a very good example of how you can look into variation principle in a slightly different way. You see, essentially Fermat's principle of least time and variation standard variation principle, as we know, as we have learned, it says the same thing. It talks about optimization of certain things, right. So, you can always draw an optical analogy if you can choose, if you have a correct picture in mind. Please go through that website. It is not exactly part of your syllabus strictly, but for me it is very important that I tell you all this and you read about it, so that you have a better understanding of the subject. Okay. Now, let us go back to the problem sets. Problem number 4 is another very classical problem, I would say. it is the problem of a catenary. Okay. So, we have a chain with a constant density and a length some density lambda, or you can take it sigma also, because lambda will be using for something else. Basically it is my mistake, I should have used sigma instead. Okay. So, let us say the length is L and it is hanging in gravitational field. Now, please remember that P1 and P2, these 2 points are not necessarily on the same horizontal plane. It could be anywhere, any 2 points in space. Okay. And so, we have to find out what is the equation of this particular chain, right. So, this is a shape which is called the catenary. Okay. So, right. So, we have a catenary here, we have a point P1, we have a point P2 and an uniform chain is hanging. So, it will trace out some curve, and the curve I think I have described it already. If it is an uniform chain, if it is an uniform thread, if it is a rubber pipe, if it is a made of steel, does not matter. If the points are in the same line, or if P1 is up, P2 is down, or P1 is down, P2 is up, does not matter, it will still follow a same type of equation. Okay. And we have to derive this equation. Now, in order to do this, what we do is we have x and we have y. Once again, I take a length dl, right. Sorry, it is not very clear. So, this length is dl and the height at which it is from the ground level is given by y. Now, what do we have to do here? What do we have to do? What we need to do is we need to minimize the potential energy of the system, because we know from the fundamental laws of physics that a system would like to go for a minimum potential energy configuration. That is the nature. The most stable configuration of a system is the configuration at which it minimizes its potential energy. Keeping that in mind, we have the potential energy V. We can write this for this particular length element is m, or rather dm g y, and dm will be sigma dl g y. I am just taking sigma because we will be using lambda for something else. So, just bear with me for a moment. Okay. I will also in the final version I will correct it. So, I will have put sigma there. Okay. So, this is your dV, and your potential energy, total potential energy of the system V will be integration sigma g, which is a constant, dl, once again you can write dx by 1 plus y dashed square times y. So, this is your function f, right. So, you have to once again write f x y y prime is equal to y root over 1 plus y dash square. Once again we see f is not a particular explicit function of x. So, del f del x equal to 0. From here all we need to do, we have to find out del f del y prime, which in this case will be y 1 plus y prime square to the power minus half into 2 y prime, right. So, y prime del f del y prime is 2 y prime square 1 plus y prime square to the power minus half, right. And we have to use the Beltrami identity once again, which is this f minus this is a constant, and once again there will be some algebra associated with it, and the final equation which I will be getting is simply this. Okay, let me give you the final equation. Just give me a second. Where is it? Oh, sorry, I'm sorry, I did not have the final equation with me. Oh, I think think it's the only way is to get this entire algebra done, but you can find it out, I guess it's not a problem. So, I really do not want to do this entire algebra now, because it will be just a waste of time. Okay. So, finally, what you will get, okay, I will give you the final answers, that is more important. So, if you follow this procedure, you will essentially get a differential equation which will have an equation which will have a solution of the form y equal to a cos hyperbolic x by a. So, this will be the final answer if you set up the differential equation from here, from this relation, taking this side as a constant some c. So, you will get this, where a is a constant which is obviously something which you can evaluate, that is not a problem. Now, this is an hyperbola, the equation of an hyperbola, this curve will follow, that is all good. Now, there is another condition given. If you look at the problem carefully, there is another condition given here, that is the length is given as L. Okay. Now, how do we include that into the equation? That is the question. Now, if we include this, if we want to include this into our equation, what we need to do is, okay, I will just remove this bit. This means if I specify the length, total length, that means L is equal to integral dl between point 1 and 2, and we have this integral. So, that is something which is given, right. Now, what we can do is we can use Lagrange's multiplier like we did. So, this is a constraint condition actually. Okay. So, to include the constraint into this equation, into the final function, what we can do is we can multiply this relation with a constant lambda, add this or subtract this from this particular expression, and we can get a function f x which is actually see dl will be nothing but integration dx root over 1 plus y dash square, right. Or I will just write it in here so that you can see. So, this is one equation, and the second equation is L equal to integral dl, which will be integral dx root over 1 plus y dash square, or sorry. Okay. Now, if I multiply this with a constant lambda, which is the Lagrange's undetermined multiplier, try to construct a function which includes this, our final functional form will be f of x, y, y prime and lambda will be given by okay. So, root over 1 plus y dash square will be the common factor in this 2, and we will have y plus lambda. So, this will be my expression for f, and just like we did before, we have to find a differential find out the set of equations, differential equation which will include both lambda. Now, if you do that, thankfully, even if we do not do that, this procedure, this elaborate procedure, nothing changes, because the final expression what you get from by solving this equation is once again y is equal to some constant a plus this lambda will come here, lambda plus a this exact same expression cos x by a plus another additional term b, which will be associated with your length, total length L. Okay. So, just give right. So, including this function or including this constraint condition with or without this constraint condition, your equation will be the same, except in the this will be little more complicated and you will have some more terms to it, right. But the functional nature will be exactly the same. So, I would say if possible, I mean if you have to solve the catenary problem for an understanding of your own, just use the first procedure. But if you have to include length at some point, then you have to follow this procedure. So, from here also we can get an equation, differential equation, which is slightly complicated, but nothing difficult. Of course, if you can find it in almost every standard textbook, and in some of the places both the procedure has been done. Okay. So, with this we are done with this problem. Last problem, there is one more, but the time is little short. So, what I will do is I will just wait, I will keep it for the next lecture, and in next lecture we will be starting small oscillation. Thank you.